Is the screen?
Yeah, it's working.
It's working.
So the last speaker of this morning session is Jihoon Hyun. He's going to talk about computing the Mandelbrot set reliably. So please go on.
Thanks for introducing me. Hello, this is Jihoon Hyun, and in this talk, I'm going to talk about the computing the Mandelbrot set reliably. Content is as follows. First, I will talk about the details, the theoretical backgrounds about the Mandelbrot set, to talk later about how to draw the Mandelbrot set. In other words, I will explain the algorithm of how to draw the Mandelbrot set reliably. First, what is a Mandelbrot set? Mandelbrot set is a set set of a complex plane which the absolute value, the point C, for the complex point C, which for all k, the absolute value of pc to the k of c is bounded. And there is one well-known proposition that if the complex number c is not in the Mandelbrot set, then this is equivalent to there exists some k, natural number k, that the absolute value of pc to the k of c is larger than 2. Well, with this proposition, we can draw a figure of a Mandelbrot set, as shown on the right. However, this proposition is not sufficient to draw a set because it only checks if the point is in the exterior or the complement of the Mandelbrot set. Also, many programs that calculate the Mandelbrot set or draw the Mandelbrot set uses floating point numbers, so it occurs a rounding error. Now I will go into details, but before that, I will show the references. Okay, thanks. I really got a lot of help from these. So, okay, now I'll start. First, we will define the period and the attracting cycle. Let z of I be the fixed points of p to the k, and then the z0 is the periodic point for p if there is some k, natural number k, that p to the k of z0 equals p0 z0. And we call the k is the period of z0 if that k is the smallest such number. If z0 is a periodic point for p with period k, then the set z0 to zk minus 1, where zj equals the p to the power of j of z0, is called a cycle. And the derivative of the p to the k of z0 is called a multiplier of the cycle due to the following reasons. Finally, the attracting cycle is a cycle whose multiplier is less than 1. Now we defined the attracting cycle. We will define the union of the hyperbolic components of the Mandelbrot set, or simply hyperbolic components, at least in this talk. The hyperbolic components is the set of complex numbers which PC has an attracting cycle. Now there are a few facts about the hyperbolic components. The first one is that the hyperbolic component is an open subset of the Mandelbrot set, and the second is that the boundary of the Mandelbrot set is contained in the closure of the hyperbolic components of the Mandelbrot set. Oh, did I mention that the Mandelbrot set is closed? I don't think so. Anyway, there is also one conjecture which is called the hyperbolicity conjecture, that the hyperbolic components of the Mandelbrot set is equal to the the interior of the Mandelbrot set. This is quite important, but I'll discuss in details later of why this is important. Now, Peter Hertling gave two propositions in his paper. One is that the complement of the Mandelbrot set is semi-decidable, and the other is the hyperbolic components is semi-decidable. However, he didn't actually merge these two algorithms. So I'll explain I'll combine these two algorithms to draw the Mandelbrot set later. Now, about the drawing. We're going to draw a set in R squared which is equally spaced R times R grid on 0 to 1 times 0 to 1 by coloring each pixel with some color. In many cases, covering the set is the most common method. In many cases, many previous researchers adopted such method. However, I'm not going to use this method, and I'm trying to use some new method to draw the Mandelbrot set. There are three. I'm going to show three kinds of colors, which I call positive, negative, and zero. Pixel meets a set if the color of the pixel is positive. Pixel does not meet a set if the color of the pixel is negative. Pixel contains a point which is close enough to the boundary if the color of the pixel is zero. Now, be careful, because even if the color of the pixel is positive, it may not meet a pixel. The converse is not true. Now I will go straight to the examples, and it will be easy to see that these two the drawings are actually the drawing of x squared plus y squared is less than 1. Okay. Why are we going to use 3 colors instead of 2? Because as I explained before, the hyperbolic components is an open subset of the Mandelbrot set, and the boundary of the Mandelbrot set is contained in the closure of the hyperbolic components. This means that the boundary of the Mandelbrot set is actually the intersection of closure of the hyperbolic components and the complement of the Mandelbrot set. This property gives a simpler, the three color approach gives a simpler approach to draw a set. In other words, we can draw a set without calculating. Okay. Yes. Now we have talked about the theoretical backgrounds. Now I'm going to talk about how the algorithms of drawing the Mandelbrot set. I didn't explain the algorithms yet, but let's look at the theorem first. If the hyperbolicity conjecture that the hyperbolic components equals the interior of the Mandelbrot set is true, then the algorithm halts and returns a drawing of the Mandelbrot set. Well, yes. Now let's look at the brief of the algorithm. First, we're going to initialize, then choose the points in the pixels and color the pixels negative or positive. And I'm going to make a helper grid, then color the grid negative or positive. Then I'll color the points made in the second part 0. And finally, iterate the 6 until all pixels are colored. It won't make sense at first, but I'll talk in details after looking at this picture. This is the 50 times 50 drawing of the Mandelbrot set with using the algorithm. The reddish reddish pixels represent the complement of the Mandelbrot set. The greenish pixels represent the Mandelbrot set. The green large one and the green small one, in other words, represents the Mandelbrot set. The colors get bluish as the iteration count of the big loop, which was described as a tab here, increases. Okay, then let's look at deeper look into the algorithm. First, we're going to initialize. Let the color of every pixel as unknown. What do I mean by unknown is that the color is not 0, not positive, or not negative. It is just just an unknown color yet. Now we're going to choose points. Oh, by the way, I'm using an example of x squared plus y squared is less than 1, but it should apply the same for the Mandelbrot set. For each pixel with unknown colors, choose a point in the pixel. Then the closure of the union of chosen points in each iteration should be the corresponding pixel. If the word is too hard. In other words, the closure of the set of all iterated points of one pixel should be the pixel itself. Okay, so next is to color negative. If the selected point is known to be in the exterior, then color the pixel negative. And similarly to coloring the positives, if the selected point is known to be in the interior, then color the pixel positive. I colored negative first, then color positive because calculating for the negatives takes much shorter times than calculating for the positives, at least for the Mandelbrot set. Now we're going to make a helper grid. Helper grid in the figure is described as black dots on the left figure. Choose a set of equally distant points. The points should get denser as the number of iteration increases. For example, I chose 4 times 4 here, but maybe in the next iteration, it will get as 8 times 8 and so on. Now we're going to color the helper grid. Color the points from previous step as we colored in steps 2 and 3. In other words, color the helper grids positive or negative. Now, using the helper grid, we're going to color the white points we chose in step 2 and 3 as 0. Color the point W, I mean the white points W 0 if there are at least one red point R and one green point G, which the distance of each point is less than 1 over R. Finally, we're going to iterate it again. do this progress until all pixels are colored. Now, I was talking about the examples with the circle. Now it's time to talk about the Mandelbrot set in details. How are we going to check if the point is in the exterior or the complement of the Mandelbrot set? Here is a pseudocode of checking if the point is in the complement of the Mandelbrot set. First, let k be 1, and while k is less than n, check if the absolute value exceeds 2, then return true, or else return false. This immediately derived from the proposition 1 that I first explained while talking about the Mandelbrot set, so it should be clear. And we're going to check if the point is in the interior. Assuming that the hyperbolicity conjecture is true, which was that the hyperbolic components of the Mandelbrot set is equals to the interior of the Mandelbrot set, we can check that C is in the Mandelbrot set. I mean the interior of the Mandelbrot set, using the hyperbolic components. Let P of x initially be x, and let k be the natural number 1. Until k becomes n, we're going to compose the polynomials. I mean, we're going to compose polynomial p and let the array of fixed points as roots. Then for every element in roots, if p derivative of p of r is less than 1, then return true. If not, if the while loop ends, then return false. Well, now it should be interesting if the algorithm terminates. So I'll give a sketch of a proof that the algorithm really terminates, assuming the hyperbolicity conjecture. Assume that the point is in the boundary. If not, the point will be classified positive or negative. It is easy to see that the algorithm terminates when the point is not on the boundary and iteration count is large enough. So anyway, so assume that the point is on the boundary. And if recall that the boundary of the Mandelbrot set is the intersection of the complement of the Mandelbrot set and the closure of the hyperbolic components. And also note that the any circle at x in the boundary of M Mandelbrot set contains a point of both the closure of, I mean the hyperbolic component and the Mandelbrot set. I mean the complement of the Mandelbrot set. This should be enough for the sketch of the proof for the termination. Also, I provide the link for the implementation, so please check it out. Finally, I'm going to talk about the evaluation time for the algorithm. The result is of the evaluation time is exponential as far as I see until 50 times 50 resolutions. the evaluation time should depend on the details of the implementations of the algorithm, but mainly the three bolded parts of the algorithm described here takes a large portion. Coloring positive calculates the root of the polynomial, which has exponentially growing degree. Root finding also takes a long time, so therefore consumes a large portion of time. Coloring points of the helper grid does the step 2 and 3, or the coloring negative and positive again for the helper grid. So it also takes a large amount. It takes a large amount of time. Finally, coloring 0 also takes a large amount of time because it should check for all the points that are colored positive and negative. This should be the end of the talk. And do anyone have any questions?
So thank you very much for your talk. Yeah, so we have time for questions. I guess that there is no work on the complexity of the Mandelbrot set. I mean, we don't know whether it's computable, but maybe assuming this conjecture, hyperbolicity conjecture, is there any work on the possible complexity?
I'm very sorry about that.
No, I guess maybe it's not possible to do that if we don't know whether it's computable. I'm not sure.
The main what I have done through this talk is that I could draw the I could draw the I could give a rigorous algorithm to draw the Mandelbrot set. And actually, that's it.
Yeah. No, I was asking whether you know whether people have studied, because people have studied the complexity of Julia sets, for instance.
Yes.
But what about the Mandelbrot sets?
I'm assuming that the hyperbolicity conjecture is true, so sorry.
And so on your efficiency graphics, what was the scale of the time? So how long did it take to make this picture, for instance?
It took around for 50 times 50. It took about 100,000 seconds, maybe. Yes, 100,000 seconds.
Okay, so one or 2 days, something. Okay. Is there any other question? No. So thank you again, and many thanks to all the speakers